For part 2, we're talking about iodine. So far, iodine 131 is a radioactive material, again, so it decays according to this equation. Now, they use A here instead of P, but it's the same, where P not the initial amount present, A the amount given at time T in days. Now, in this case right here, we are given the rate. That's this right here, it's rate. And it is negative because it's going to decrease. Half-life means it's going to keep decreasing over time. So the first question says, what is the half-life? Now, to do this one, I'm going to set up my little variables, A naught, R, and T. Now, it doesn't give me how much I started with. And that's the problem here. So we're not told how much we're starting with. So how much do we start with? I don't know. So this is your choice. You get to make up a number. I keep it simple. I make it 100%. Whatever we started off with is 100% of whatever we started off with. So that's our A naught, 100%. So A, if it's half-life, has to be 50. Now the R they already gave us, this negative 0.087, and we're looking for how long that will take. So I plug it into my formula. 50 equals 100 e to the negative 0.087 t. And I solve. Divide by 100, 0.5, hence the phrase half-life. We wind up with exactly half of what we started with. I know. Take the natural log to get rid of the e. Natural log of 0.5 equals, that's going to bring down the power. We get to get negative 0.087 t. And then we just divide. We take the natural log, let me clear that out. Natural log of 0.5, and I divide that by negative 0.087. And we get about 7.967. And it's going to be, what is that going to be? What unit are we in? Does it tell me? Days. Yep, there it is. Days. So in about 8 days, we'll have half the iodine remaining. So that's kind of cool, huh? How long will it take for 100 grams to decay to 10 grams? That's P, not, that's P. So if I write out P is 10, P naught, what am I starting with? 100. R, we know is negative 0.087. T, I'm still looking for how long it'll take, so still looking for time, very common. So this time we get 10 equals 100 e to the negative 0.087 t. And then I just solve. Divide. That becomes 0.1 e to the negative 0.087 t. Take a second, get a calculator. We get the natural log of 0.1. That's going to equal 0.087 t. Yep, forgot my negative. And I divide. That's all. I just divide. Let's take a calculator. I'm going to take the natural log of 0.1. Divide that by negative 0.087. And we get about 26 days. About 26.466 days. So it'll take about 26 days to get down to 10 grams. And we can do that. And scientists know this exactly. That's why carbon dating is so cool. I mean, carbon dating is carbon's half-life is 6,730 years, around there, something like that. And they can use that to determine the age of bones. And it's accurate to within 50 years. So it's a very good way to use. Now, how do they determine how old the Earth is? Well, the Earth is billions of years old, if you believe all the hype. So how do they determine how old the Earth is? They have to look at other elements. There's not enough carbon remaining from the beginning, early Earth phase. So they might look at something like potassium. Radioactive potassium has a half-life of 1.3 billion years. So if 10 grams is present now, how much will be present in 100 million years? And that's a good question. Now, the one they didn't tell us, though, is the rate. So since they didn't tell us the rate, the first thing we do is we got to find R. And how do we find R? They gave us half-life. So how much am I starting off with? Well, let's go ahead and use the 10 grams. I start off with the 10 grams. I'm going to wind up with 5 grams. R is what I'm looking for. T is 1.3 billion. Okay, that's going to be fun to write in the calculator, isn't it? So when I set it up, 5 equals 10 E. All right, let's do a billion. R, 1, 2, 3, that's 1,000. Million. Billion. Okay, divide and get 0.5 equals E to the 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 R. So the natural log of 0.5 equals 1, 2, 3, 4, 5, 6, 7, 8 R. Let me just double check. Hundreds, thousands, whoops, hundreds, thousands, millions, billions. That's right. All right, so R equals, now it's going to be really small. We're going to try to be as accurate as we can. Okay, so take the natural log of 0.5, divide that by 1, 2, 3, 4, 5, 6, 7, 8. Now notice, I'm going to write this as accurate as I can. This is, R is about negative, go out 10 decimal places, 5.332 times 10 to the negative 10. Wow, that is small. Okay, so I write out my equation. P equals the initial amount, 10, E to the negative 5.332 times 10 to the negative 10, T. And I want to find out how much is going to be left when T is 100 million. Okay, so I plug it in. 10e to the negative 5.332 times 10 to the negative 10 times 100 million. Don't let big numbers scare you, okay? The calculator is going to do all that nasty work for you anyway, so I don't worry about big numbers. Big numbers don't fear me. I got a calculator. All right, so I go 10e, and I'm going to type all of this in. Negative 5.332. Use the E button, second, comma, E. That's scientific notation on the calculator, okay? Negative 10 times 100 million. And I get 9.481, wow, grams. Is that right? Grams. Wow, in 100 million years, we only lost half a gram. A half a gram. And that's why they can use other elements like radioactive potassium to determine the age of dinosaurs. They can use potassium, you got uranium, they can look at the soil around it, look at the uranium content, and things like that to find out how old the Earth is. And they have other elements for dinosaurs. That's not, they can't even use that for dinosaurs. That's too big of a half-life for dinosaurs, so it's kind of crazy. All right, so what I would like you to do right now is go ahead and try number 5. So pause it right now and try number 5, and then come back and we'll take a look at it. All right, enough of a break. The population of Midwestern cities follow this model. The population decreased from 900,000 to 800,000 in 2 years. What will be the population in 2020? So what we got to do is come up with the rate, and that's easy. We get P, P naught, R, and T. We know the time. It took 2 years for the population to go from 900,000 to 800,000. We're looking for the rate. I just type it in. 800,000 equals 900,000 e to the r times 2. So I divide, I get 8/9 equals e to the r, or 2r, or ter. So we take the natural log of 8/9, and that equals 2r. So we can find r. Just type it in your calculator. Ready? The natural log of 8/9. Divide that by 2. That's not 25, that's 2r. Be careful. So r is negative 0.059. There's my rate. Once you get your rate, now you can come up with, now you can answer the question. P, P naught, R, T. What will the population be in 2020? I'm looking for the population, given the initial population of 900,000, R, negative 0.059, and T, we know, I'm starting in 2012. I'm starting in 2012. I'm ending in 2020. That's 8 years. Boy, awful. That's 8 years. Don't start in 2014. We're starting in 2012. Okay? So in 8 years, what's the population? Well, type it in. P equals 900,000 e to the negative 0.059 times 8. And I just type that in our calculator. 900,000 times, well, just don't do times, e to the negative 0.059 times 8. And I did this. P equals 561,378.162. But it's people. We don't worry about that. It's about 561,000 people. All right. So that's part 2. So make sure you try these out if you need to again, and we're going to practice more of these in class tomorrow. Thank you.